Good afternoon. I am Seong-Eun from Yonsei University, Korea. I'm going to present about our work that is entitled as MaDeNet, Disentangling Individuality of EEG signals through feature space mapping and detachment. EEG signals are popularly used for the analysis of perceptual user states in many studies. However, each signal's significance vary depending on individual, which becomes a critical obstacle to generalized modeling. These studies showed the difficulty of constructing the generalized model across the subjects. The left figure describes the classification accuracy for binary emotional state classifications depending on the level of subject independency of features. The classification performance decreases as more generalized features are employed. The right figure shows the classification results about the source type of emotion in a subject-wise manner. We can see the high variance of classification accuracies across the subjects. There have been previous studies to overcome the individual difference of EEG signals so we can maximize the classification performance of the generalized model. Some previous studies aimed for finding the features that are robust across the subjects, which can be achieved by designing a novel feature or by selecting the robust features from a large feature set. Approaches of another type tried to modify features to be robust across subjects. Some studies proposed an adaptation method for subject-dependent features so the features can be applicable to another subject. Another approach to remove the individual difference is detaching the subject information from EEG signals. For example, the subject information is given as the additional condition for autoencoding in this figure, so that the autoencoder can extract the representative features of EEG signals regardless of the subject information. These previous studies are assuming that the subject-related information and target-related information is separable directly from the handcrafted features or raw EEG signals. However, raw EEG signals contain a large amount of noise, and handcrafted EEG features are not optimized to their given classification task. Therefore, it is not assured that the target perceptual state and individuality of EEG signals are separable. So we propose a novel deep learning approach for EEG signals to effectively disentangle the subject-related information. We named the approach as MaDeNet because the network conducts the feature space mapping at first and then detaches the subject-related information. We also designed a new entropy loss for the feature space mapping, which enables to obtain the classification task-aware feature space. So let me explain about the system. We employ the 3D matrix of connectivity values as input data. The input data undergo the feature space mapping at first. The output of the feature space mapping network, Z, is then inserted to the detachment network and entropy calculator. The obtained features are used for the target classification. The user identification is also conducted using the same features. In a backward path, the target classification loss is used for the training of the target classifier, detachment network, and feature space mapping network. The user identification loss is used for the training of the user identifier, and the detachment network is trained based on the inverse user identification loss. The entropy loss is used for the training of the feature space mapping network. So the learning scheme can be summarized like this. And the lambda 1 and 2 indicate the weight values to balance the contribution of two different losses for the learning. The entropy loss is calculated by using this equation, where the capital letters of K and C indicates the dimension of the vectorized Z and the number of target classes. The PKC refers to the ratio of some feature values for the kth component of Z for the class C and that for all classes. Therefore, minimizing this entropy value makes each component of Z activated only for a small number of target classes. Thus, it becomes classification task aware. The detachment network is trained based on the target classification laws and inverse user identification laws. Therefore, the extracted features by the detachment network become effective for the target classification and at the same time unrelated to the subject's identity. So in this work, the feature space mapping network and the detachment network are implemented as the convolutional neural networks with 2 convolutional layers and 1 max pooling layer. And we used fully connected layers for the target classifier and user identifier. The lambda values are assigned as 0.01 and 1, which correspond to the roughly equal contribution of the losses. The weight values of the user identifier are updated at every 10 outputs of the training of the other networks. The deep database is used for the experiment, which contains the 32-channel EEG signals obtained by watching emotional music videos. The EEG signals were measured for 32 subjects and 40 videos. We defined the learning purpose as to classify which video was shown to the subjects while the EEG signals were measured. Therefore, the experimental problem becomes the classification between 40 classes. The phase locking value that measures the phase synchronization between 2 signals is used for calculating the connectivity values. The 1 minute long EEG signals are divided into 3 second long segments with an overlap to increase the number of data. So then let me show the results. This figure shows the classification results that were obtained by using different networks. When a simple CNN is used for the feature extraction, the classification accuracy of 72% is obtained. Disentangling the subject-related information significantly increases the classification accuracy to 84%. The feature space mapping further enhances the classification accuracy. The classification accuracy of 86% is obtained in this case. MaDeNet also includes the entropy calculator, which enables the classification task-aware feature space mapping. As a result, MaDeNet achieves the classification accuracy of 92%. So we can conclude that the classification performance is noticeably improved by using the proposed method. Furthermore, we compare the classification results of the simple CNN and MaDeNet depending on the subject. It is remarkable that the MaDeNet does not only improve the classification performance, but also reduces the performance variance across the subjects. For example, the simple CNN shows the degraded classification performance for the subject 11, 22, and 25. But MaDeNet results in the comparable classification accuracies for those subjects. This indicates that the subject information is effectively detected by using MaDeNet. Okay, then let me summarize the presentation. In this work, we propose MaDeNet, which consists of feature space mapping network with a new entropy loss and detachment network. This is to effectively disentangle the subject-related information included in EEG signals. We demonstrate the effectiveness of the MaDeNet based on the video classification problem. We also show that the individuality of EEG signals is effectively discarded by using the MaDeNet. This is the end of the presentation. Thank you for your attention. And if you have any questions, please contact me at this email address.